We begin our 8-week course reading about science as a methodology and discussing how fossils are formed and found by the scientists who study them, called paleontologists. Then we look at how paleontology takes a cross-disciplinary approach to learning the history of life on Earth, specifically addressing how we apply ages at points across that history and the dynamic nature of Earth itself across deep time. The most obvious pieces of evidence we have for learning about dinosaurs are their fossil remains. Body fossils are skeletal remains, bones and teeth for the most part. Usually these skeletal remains are found as isolated elements, a bone here, a tooth there. This is because the skeletal remains of vertebrates usually become disarticulated, separated into pieces by scavenging, decay, and weathering. Bones and teeth that become fossils were necessarily buried, and the sooner they were buried, the better their preservation tends to be. Once buried, they begin the process of permineralization, with the pores and vacuities within the bone becoming filled with other minerals. Paleontologists prospect for and collect these fossilized bones and teeth in the field and bring them back to be curated into museum collections, usually spending time in the care of a preparator who cleans away the rock matrix, stabilizes, assembles, and restores the fossil. In addition to body fossils, we have trace fossils. These are fossilized traces left behind that are not explicitly part of the organisms that left the traces. These can be footprints, trackways, skin impressions, coprolites, which is fossilized scat, or even structures purposefully built by organisms like tunnels, burrows, or nests. These are often considered forms of fossilized behavior, allowing us to observe indirectly the actions fossil animals may have performed in life. In addition to fossils, paleontologists use evidence from a variety of other scientific disciplines to unravel this grand mystery. For example, we combine the disciplines of sedimentology with paleontology to conduct inquiries into the realm we call taphonomy, which is the study of what happens to an organism between the time it dies and the time it is found in fossil form, jacketed, and collected. To even decide where to begin looking for fossils, paleontologists need geological maps that represent the surface geology of a region, including the kind of rocks that are preserved at the surface, as well as their age. Paleontologists hunting for dinosaurs, in particular, are going to look for rocks that are sedimentary as opposed to igneous or metamorphic rocks. Sedimentary rocks are formed as sediments deposit in horizontal layers and are eventually deposited on top of themselves. Dinosaurs are more likely to occur in sediments that were deposited in terrestrial environments, those on continents as opposed to marine environments, which are formed at the bottom of oceans and seas. To make maps that demarcate strata, specialized geologists like sedimentologists who study how sediments deposit and become stone have studied the exposed geology across Earth's surface and determine not just the type of rock exposed at the surface, but even the age of those rock units. Which brings us to another important consideration for hunting dinosaurs, the age of the rocks. Dinosaurs lived during the Mesozoic era, which is comprised of 3 geologic periods, the Triassic, Jurassic, and Cretaceous. This means the rocks in which dinosaur fossils will be buried must have formed of sediments deposited during one of these 3 periods. These periods were originally defined using the relative dating techniques afforded by some of the founding principles of geology, like superposition, original horizontality, and the principle from which biostratigraphy is derived, faunal succession. Using biostratigraphy to follow distinct assemblages of organisms through time and across continents, we can correlate strata from across the globe together and get a view of what different regions of the world were like, or linked, millions of years ago. However, as I mentioned, these are means of applying relative ages to strata. That means we can figure out which strata are older and younger than others, but we need another tool to apply an absolute or numerical age to strata, and to the fossils preserved in those strata. This is where nuclear physics comes in. Radioactive isotopes decay over time, emitting particles as each radioactive atom changes on its way to becoming a stable atom. The speed at which radioactive isotopes decay is a measurable and known value thanks to testing through a few different methods including mass spectrometry and electron spin resonance. We calculate and define radioactive decay rates in terms of half-lives. Each radioactive isotope has its own half-life, which is the amount of time it takes for any given sample to change half of its radioactive atoms through a decay event. Carbon-14, for example, has a half-life of 5,730 years. That means half the carbon-14 in a sample containing carbon-14 will decay every 5,730 years. After a number of half-lives, the ratio of undecayed isotopes to those that have already decayed becomes too small to accurately measure. This is why radioactive carbon is not useful for dating dinosaur remains, but instead was popularized through its use in archaeology. Paleontologists rely on isotopes that decay more slowly, like radioactive uranium, argon, and a few other elements. These isotopes have half-lives measured in millions to billions of years. The discovery of radiometric dating comes from the hunt for a means to calculate the age of Earth itself. Early calculations were made by Lord Kelvin by estimating the rate at which Earth had cooled since its initial formation. Physicist Ernest Rutherford, who compiled the first complete theory of radioactivity in nuclear physics, pioneered the use of radioactive decay as a means to ascertain the age of rock samples. His measurements of hundreds of millions of years from some samples were much greater than Lord Kelvin's own calculations, and as a young upstart in physics, Rutherford had to tread carefully, proposing his hypothesis. With the estimated age of the Earth greatly expanded, the planet and its history could begin to be perceived in terms of deep time. The changes that could occur over such vast expanses of time were much greater than when people thought the planet was just thousands to millions of years old. Mountains could build and erode away, seas could form and disappear. The very shape of the Earth could begin to be seen as plastic, a changeable thing. This line of reasoning sparked inspiration in the mind of a talented German meteorologist named Alfred Wegener. He noticed that the shapes of Earth's continents could be rearranged to fit together in a sort of enormous puzzle. All 7 continents had margins that aligned and could theoretically at one time have been a single continent that split apart. His revolutionary idea was published in 1912, but was met with heavy skepticism, mainly because he had no source for the forces that would have been necessary to move continents. The liquid nature of Earth's molten core and mantle was not understood at the time. The continents were thought to rest on yet more solid rock. His hypothesis of continental drift did not seem complete enough for many and remained a sort of fringe idea for decades. Not until we understood more clearly what was happening at faults and continental plate boundaries did Wegener's idea make sense to everyone. Along these boundaries, deep beneath the sea, it was learned, new crust is formed and old crust is recycled. Divergent faults spread, and magma rises to the surface, is quickly cooled, and continues to push the fault apart. Convergent faults smash into one another, driving one plate under another, forcing the plate underneath to be subducted, remelted, and recycled into Earth's molten mantle. These forces act to move continents across Earth's surface. As recently as the Triassic, all of the continents were coalesced into a single supercontinent called Pangaea. Over the course of the Mesozoic, the continents broke apart. They first spread into 2 multi-continental landmasses, Laurasia in the north and Gondwana in the south, through the Jurassic. Laurasia was composed of North America, Europe, and Asia, while Gondwana was a conglomeration of South America, Africa, Australia, Antarctica, and the Indian subcontinent. The continents reached a configuration approaching that which we have today by the end of the Cretaceous.